I want to look at a special type of substitution we'll run across involving trig. But to do this, I want to remind you of a couple of trig identities. Hopefully I'm reminding you and not teaching you something you've never seen. Sine squared of x plus cosine squared of x equals 1. Now, this is called the Pythagorean identity. There are two others. If I take this and divide through by sine squared, I will get 1 plus cotan squared x equals 1 over sine, which is, cosecant squared x. If I take this equation and divide by cosine squared x, I get the Pythagorean identity 1 plus, no I don't, I get tan squared plus 1 equals secant squared x. I tend to remember that tan and secant like to hang out and cotan and cosecant like to hang out. Okay, so how do we use this? Well, if we had the integral of sine squared x cosine x dx, I can see I've got basically u squared du. I can just do the power rule because I've got the derivative sitting right there. But on the other hand, what if I had, say, sine cubed x cosine cubed x dx? Well, I have the derivative, but I've got 2 left over. So that's where the Pythagorean identity comes in. I'm going to need one of these for the derivative. I'm going to let u equal sine, but then I'll have 2 extra cosines. And what I'm going to do, sine squared x, and then I have the cosine x dx, and the other 2 I'm going to rewrite as 1 minus sine squared x. So if I let u equal sine x, du is cosine x dx, then this becomes the integral of u squared 1 minus u squared du. To integrate that, I multiply through, and then I do my power rule. U cubed over 3 minus u to the 5th over 5. And my u is sine x. What about the other 2? Well, what if I have the integral of tan to the 5th x secant squared x dx? Well, like before, I can see that the derivative of tan is secant squared. It's sitting right there. I will have tan to the 6th of x over 6 plus c. But it gets tricky when you've got different powers. Let's say I had tan to the 5th x times secant to the 4th x dx. Like before, I'm going to use some of it for the derivative, and I'll use the other to rewrite using the Pythagorean identity we have, this one over here. So I still have tan to the 5th x. I'm going to use 2 of the secants and rewrite that as tan squared x plus 1, and then I have secant squared x dx. This will give me, if I let u equal tan x, du is secant squared x dx. So I get the integral of u to the 5th times u squared plus 1 du. Multiplying through, u to the 7th plus u to the 5th. And doing my power rule, I get u to the 8th over 8 plus u to the 6th over 6. And my u was tan x. Another problem we come across is when we can't switch one into the other and we need to figure something else out. So let's say I have two other identities before I do that. I know that sine squared of x is 1/2 1 minus cosine of 2x, and that cosine squared of x is 1/2 1 plus cosine of 2x. And you may or may not have seen that, but now you've seen it. This is how we deal with squares that don't have the derivatives floating around. So if I have the integral of sine squared x dx, can't do the power rule because I don't have the derivative sitting over there. I need to shake it up and get something different. So I'm going to rewrite it using this formula over here. This is 1/2, get that out of my hair, 1 minus cosine of 2x dx. This I can integrate. No u's involved. And we can multiply through, or we can just leave it like that. Let's just leave it like that. This will also come up if you have both of your sines and cosines are even powers. You can't use one without the other. You have to have odd powers to peel one of them off to be the derivative. It's a little bit different with tan because the derivative of tan is secant squared. The evens are okay there. And the first thing I'm going to see is tan squared x dx. Well, this isn't so bad because tan squared is secant squared x minus 1. Just rearranging that formula. Integral of secant squared is tan x minus x plus c. If I have, say, tan cubed of x secant cubed of x dx, well, what can I do with this? I could rewrite this, and I need two of them to be the derivative if u is tan. But then I have an extra secant floating around that I don't know what to deal with, and I'll be multiplying it through. Or I could let u equal secant x. So du is tan x secant x. Sorry, I kind of wrote that in a weird order. So what does that leave me with? I'm going to use one of my tans for the derivative. So I've got a tan squared x. I have a secant squared of x times a oh, this is a mess. This is not, I'm not explaining this very well. So I will use one of the tans in the derivative. I have two left. And I know that tan squared of x is equal to secant squared x minus 1. So, two of my tans will become secant squared x minus 1. Beware, Catzilla is showing up, I think. Then I have another tan x that I'm not playing with yet. And then I have 3 secants left. So I'm letting u equal secant, so this becomes u squared minus 1. I will use one tan and one secant for the derivative, so that becomes my du. And I'm left with 2 secants, so that's u squared. Hopefully that makes sense. Multiplying through, I now have u to the 4th minus u squared. I can do my power rule. My u, what was my u again? Secant x. My plus c. So there's some weirdness going on with the trig that I wanted you to see beforehand. We'll play with it more on Tuesday. I thought I would start integration by parts, but I don't think I'm going to start that until next Thursday. So, hope you have a great weekend, or when you watch this, the weekend will probably be over. Later days.